Okay, all right, what's up? Okay. Okay, exactly. I'm very happy to have Ashok with us again. He's a postdoc researcher at EPFL. He did a degree from IIT Bombay. And Volker about his thesis advisor. And went to Illinois for his master's and PhD. And since then, he has been at EPFL the last couple of years. He's won several awards and fellowships in his short career, including the Affiliation Best Paper Award. And Ashok.
Thanks for the nice introduction. Hi everyone, I'm excited to be here. So today I'll be talking about my past research work that actually broadly in the space of data science. So yeah, let's get started. You might have to, oh, it works. So yeah, this is like my brief academic background. I did a couple of institutes. So like I did my bachelor's with Professor Vivek Vogel in the field of stochastic optimization. Then master's I worked with ECOM, like in hardcore information theoretic inequalities. Later I shifted broadly to the intersection of machine learning and information theory with Pramod and Sevu. And currently for postdoc working with Michael, trying to do everything, but not really. So yeah, this is my brief background. And with regards to like the research overview, the main philosophy behind most of my works is like for practically well-motivated problems. On one hand, I try to design like theoretical frameworks so that it's a clean way of looking at these problems. And at the same time, on the algorithmic front, I use data-driven solutions in order to come up with computationally efficient solutions. And this kind of framework allows for a natural interplay between theoretically well-established fields and at the same time data-driven algorithms. So that's forms the title as it says. So the theoretical frameworks for practically well-motivated problems during the solutions and the solutions given by the data-driven algorithms, and this nice interplay of theory and algorithms allowing to study this problem from a more grounded point. Okay, so this is the philosophy. And so today I will talk about this philosophy action for two different domains. One, I will talk about at the intersection of machine learning and information theory, where I'll focus mostly on this framework of learning codes. And in particular, I will talk about my work on Kevo codes that I did in ICM a couple of years ago. And in part two, I will talk about my work on learning optimal transport. This also appeared at the same venue a couple of years ago. And in part three, I will talk about a more recent work, which is a work in progress, about learning in the space of these large language models, transformers. And so this is an ongoing work. I will touch upon towards the end. And finally, I will conclude with some interesting future steps in this domain of using some interdisciplinary angles to study problems at the heart of data science. And so this is like the brief overview for today's talk. And in the interest of time, I will not be covering some other works of mine that broadly fall in this space. One is in the space of learning codes and decoders, few works of mine, but I would be happy to chat about later. And the same here, like my past work on mixture of experts, as well, which roughly falls at the intersection of machine learning and optimization. So so that's it. So let's get started with part one on learning codes. So I mean, in case someone is not familiar with what codes are, the natural question that comes to mind is what are codes and why do we need them, right? So this is like a natural question. So let's go about addressing the first one, what are codes? So let's say, like I was the tradition, it always means to start with Alice and Bob, and who can never stay together. So Alice wants to communicate with Bob, and let's say she wants to send a message M over there, let's say. And I mean, situation is not fair. Most of the time you have to travel through like communication noise over wireless channel. So there is some noisy channel that she has to communicate over. Oh, in the PDF, it's going blur. Okay. Yeah, she has to communicate over a noisy channel. And one way to deal with this in typical wireless communication or coding theoretic framework is there is an encoder that tries to map the message to a longer, let's say, code word. And yeah, so the decoder on the side of Bob, it receives a corrupted code word and it aims to decode the transmitted message. Okay, so this is the framework, and typically the length of the code word is longer than message so that you can combat against noise with some redundancies. So this is the typical point-to-point communication framework, and by code, I mean a pair of encoder and decoder. Okay, so this is the pair of these two, and jointly calling them as code. And the obvious and the answer to why do we need them, as you can see, we say code is good when it ensures a reliable transmission between 2 points. Right. Okay. So that's the main basic purpose of a code. So yeah. So these are codes. So now we are seeing what these are, and the framework I present. I wrote it in the point of view of a channel transmission, but for the compression as well, one could think of analogously, just that the dimensions get shortened and you want to recover them back. That's it. CD-ROMs. So okay. So this is fairly generic framework. So this is with regards to what codes are now. Okay, now this is good, but that's not the end of the story, right? We need to design some good codes in order to ensure reliable transmission. And as you can see, some of the inherent difficulty with regards to designing codes, and the obvious reason is that the space of this encoder-decoder pairs is quite large. And why is it large? So just to give an example, let's say you want to build a RAID half code, meaning you have 100 bits here and you want to transmit a block length of length 200. So the rate is half. Okay. So this is tantamount to basically saying you want to design or construct 2 to the 100 code words, right? Because for each of the 100 bits, there are roughly 2 to the 100 combinations, and each of this code word lies in a 200 dimensional. So this gives you just a simple feel for like how big the code book could be, even for like some simple medium block length setting. So this just gives like how big the space of the possible code books is, and definitely you need a reasonably good search procedures for it. So this is just to highlight what the main intrinsic challenges are. And if you take a look at historically some of the landmark codes, like starting from all the way from 50s with Hamming all the way till Polar, like LDPC, Turbo, there have been number of landmark codes that have been designed for communication over radial channel and many other settings that have been very impactful in like various regards. For example, many of these codes have been part of our global communication standards or a variety of regimes and settings. So these codes have really been impactful. But at the same time, as you can see, right, one way or the other, there is some gap between progress in the discovery of codes, right? Of course, it's not something I intended. This is the way it is. They somehow reflect like intrinsic difficulty in how hard it is to come up with some of these very good codes. And the main motivation here is, can we automate the search for the codes? Given, of course, it's a very difficult task, but is there a way we can get a handle on designing a new class of codes and better codes in a reasonably computationally efficient? So this is the main motivation for our work. And in order to get a insight into how we might go about doing it, just recall that I said code is a pair of encoder and decoder. At the end of the day, they're algorithms, right? There's an encoding mapping and it's a decoding mapping. At the end of the day, they're algorithms. And we have already seen in a completely different context, in the context of game playing, the success of data-driven algorithms, like from example of AlphaGo in 2014 or 2015. So here, if you think about it, in the setting, game playing settings, the setting is mathematically very well defined. the game rules of the game are, you can write it on piece of paper, right? They're mathematically well defined, and the goal is to, you want to design an algorithm, the game playing strategy. And we have seen in these scenarios how data-driven methods, if designed properly, can do very well. So this was from that time when he was his least role, he was world champion at the time, and defeated him 4-1 at the, that showed the potential these methods have. So in the same spirit, if you come to our communication end-to-end setting, right? It's a mathematically well-defined framework, and again the task is, as I said here, you want to design algorithm. So the hope is, can we, in this era of progress, can we traverse on this with the help of data-driven algorithms? So this is the main motivation, and in our work through Keva codes, we show that in certain regimes the answer indeed is yes. And next I will talk about how we go about doing it and how we design data-driven codes that can perform at the very cutting edge. Okay? Yeah.
So when we generally talk about codes, there is often, like even in your setup, there are about 2 to the 100 code words.
Correct.
So how should we think of, I mean, for many of these families of codes, the family is large, but it has a very thin and succinct description.
Correct.
For codes discovered through this, how should we think of, how are they described? Like, are you?
Sorry, can you discovered as in like these codes or the one?
The neural codes.
I will go about the next few slides. I will go into details about what these are. It's exactly answers roughly the same line of questions you asked, like how do we go about doing it? Okay. So
We have a punchline. Is it much better than other codes?
I mean, I cannot say like uniformly everywhere, but in certain regimes, you can outperform classical codes. But there are challenges again. But definitely, I do believe for in certain contexts, one can design a better code. Yeah.
So this is in terms of error exponent?
This is more in terms of error performance, like bit error rate and block. I cannot theoretically show that this achieves capacity, so to speak.
So it's only in simulation.
Yeah, so to speak, yes.
And it's for fixed prominence?
I will show it for the various block lengths.
Okay.
But the code that, for various block lengths, like a specific family, different traits, like I will show. One could, I mean, it's a fairly generic setup in the sense it allows for, you can pick the parameters that you want, and for that code parameters, you try something and you see if it performs well or not.
So speaking of punchlines, does KO stand for knockout?
That was the intended wordplay by my advisor, but actually KO actually means something.
Okay.
That's why I said it a wordplay. Otherwise, it's this catchphrase. Okay, so let's see what they are. So, how do we learn codes? So, if we revisit the actual point-to-point communication framework, again, Alice and Bob. So, there's an encoder and decoder. So, the learnable components here are this encoder and decoder that we want to parameterize based on neural network or something, some parametric family, and you want to train them in an end-to-end fashion. Let's say, like, if you think about it, message bits just like binary bits, right? So you can write some cross entropy loss for each bit, like just average or something. So you can write a well-defined loss function, and you can parameterize, and you can try. In principle, on paper, right, there exists a framework through which you can learn codes. Okay, but what happens? So what happens usually is that if you just use some random off-the-shelf neural, something, I don't know, some feed-forward.
And what is the loss function?
Loss function is the cross entropy loss. So cross entropy loss is nothing but a binary classification loss. Just a fancy way of saying it.
But what is the input to the loss function?
So if you, let's say message is a block length of 10. The message is like binary vector of length 10.
Yeah.
So for each bit you write the loss for binary classification loss, and you average across all the bits.
No, but your search space is not the search space of code words. Your search space is the search space of encoders and decoders.
I mean, why not just output the same thing? Like,
So the search space here is not the search space of codes.
That's
Right.
Large by itself. The search space here is the search space of encoders and decoders.
Correct.
Firstly, I don't even know how we are going to write this as I don't know how we are going to characterize this space of encoders, decoders.
This I will get to.
Okay.
Right. Like what is
So once I don't know that, then Raghu's question comes is, I don't know what is the input and output. What do you mean by cross entropy loss? If I don't know what
Cross-entropy loss achieved by a specific instantiation of an encoder-decoder pair. You fix one encoder-decoder pair and you want to know how well this is doing.
you know, no, but where is this family of encoders? It's just
That will come
right now it's an arbitrary function.
fix a encoder and decoder.
Okay, fair enough. Okay.
For a fixed code, I can measure this loss.
Okay.
This is the, how do you measure this loss? I can write on the, let's say a message is a, let's say there are k bits, right? 0 to 1. Okay. K. And the output M hat is generally its probabilities. By some p theta, I will tell what theta is something, doesn't matter. Probability that each of these bit is 1. It's also a vector. If this is then I don't know, 0 to 1. 0, 1 interval k. Okay, you have to begin with, you have a bunch of bits, in the end you have a bunch of probabilities. And the loss you can write as averaged across all the k. Yeah, m1 times, sorry, mi times log p theta, mi is 1 plus negative of this, 1 minus mi log probability delta. This is the loss.
So you're also uniformly avoiding over A, right?
Yeah.
This is for
This is for a fixed method, but yeah, because method bit the uniform is generated from the vector space.
So this is, yeah, so it averages it.
This is for a fixed, yeah, but in general you take
LM theta.
Yeah.
This is.
yeah, LM
LM theta
L theta is
is.
expectation M uniform over this hypercube. But in general practice, you always sample few and try and so take empirical discrimination.
Okay.
And what is the motivation for considering the marginals instead of the whole vector?
So very good question. As you can see, this becomes a multi-class classification problem in to the case space, which is not really thing to do. If you want to classify the full block.
No, but what I want to say is that suppose you have an encoder decoder that a pair that with probability half it outputs correctly, and with the remaining probability it outputs exactly the flip version. So if the probability half will output n, with the remaining probability will output n complement. So in this formulation, you will actually have a very huge loss because each marginal will be uniformly one half. But it's not that bad because you know it's one of two choices, so it is a bit counterintuitive to me.
So you're saying a loss that does not take into account the block aspects of it? But the way this is generated is all these bits are IIDs.
Yeah, so I'm saying regardless of how these bits are, my encoder decoder pair is such that given the input m, it outputs m with probability 1/2 and m bar with probability 1/2.
What do you mean by M? I mean, you mean the full block or is it each individual bit?
M is k bits, m is 0 into the k. It's an element of 0 into the k.
Okay.
So if this is the input, you encode it and then you decode from the encoding after the channel.
Okay.
Then with probability 1/2, you get the correct message m. With probability the remaining 1/2, you get m flipped coordinate wise.
Okay.
What is the noise model? The noise model is like every bit is flipped with some probability.
This
General channel.
for now this is generic channel. It can be done.
So okay, so now my decoder outputs either m or m complement.
Okay.
So I would say it is a very good decoder because it's only off by 1 bit. If you know 1 bit correctly, then you know the rest of the message. But in your loss function, it would say it's off in all k bits.
Yeah, that's true. That is this one. But the point is, the loss function in your case is going to become even more complicated loss function. And even for this loss function, I think it's not clear how we will do it.
It's not clear.
And they are working with a simpler loss function to begin with. Yeah.
Okay.
I agree with your
There's a
point.
lot of people with bitmap decoding and block decoding and. Yeah.
Okay, we can.
Yeah. Yeah,
Because I don't even see how to do, they will try to solve the problem, that's what you said, but I don't see how to even do it in this case.
I mean, I don't even see the formulations.
Yeah.
Okay. So this law, yeah, you fix an encoder and decoder from channel something, and for that you measure the loss. And by training, you mean you keep changing your model parameters in a way so as to minimize the loss. That's what I mean by the. Okay. And as I was saying before, if you just randomly use some neural network like off the shelf, like import PyTorch or whatever, import the colleague files. So what happens is generally they don't work as I don't know if it's expected or not, but that's a scenario in the sense saying if you just don't impose any structures, if you just randomly throw neural networks, just because they are neural network doesn't mean it will work. So that's what I mean to say. If you and it actually forget that even it ends up worse than repetition code. Repetition code is like the simplest scheme you can think of. You have a bit, you repeat it 10 times. Right? That's the simplest coding scheme one could think of. And it ends up performing even worse than such a simple scheme. So you definitely need some sort of inductive bias or structure, as a couple of audience already mentioned. And the key question is what kind of inductive bias are you willing to impose and what are the key structures that you are looking at? Okay, so that's the main. You can think of that's the main thing that's like the fourth pillar basically. That determines what kind of codes you'll end up learning. And for the inductive bias, so what we will particularly what we look structure that we look into is something called a Kronecker operation or KO as so KO or the Kronecker operation, and one of the reasons why did we choose this, and the structure lies at the heart of some very well-known codes like Reed-Muller and Polar code. Actually, both the codes have this kind of a Kronecker structure, and these codes are already known to be very good in a variety of scenarios, as we already saw. And that's one of the reasons why we wanted to use this structure as an anchor in order to build the code. Okay. So now I will talk about what exactly this structure is. So
will you at some point tell us like what are the inputs to your neural network and what does
then the next slide. So as you can see, just to keep in mind, the input is always a message block, bunch of bits.
The input to neural network is just going to be a message.
Message.
Okay.
To think, you can think of 0 to 1, but in practice, plus minus. Doesn't matter. It doesn't matter. Just bunch of plus and minus 1. Maybe we can keep it at that level. They're all plus or minus 1. That's the message. It's exactly as it is. Encoder output is something.
But for a neural network, the input is going to be a message.
Input is always a message. Encoder, yes. For the encoder, input is always a message.
For the next slide,
fine. Okay, that's okay.
Yeah. Okay. Now I said what the Kronecker structure is. So here, this is how the encoding or encoding structure for both Reed-Muller and Polar codes looks like. So I wrote it as a complete binary tree, and as you know, like Kronecker operation can be viewed as some sense a binary tree. You keep recursively doing the same thing, and that function that's at the heart of these codes is something called a Plotkin transform. And this Plotkin transform is given by the following. So it does the following transformation. Whenever you take 2 bits U and B, it computes U and you XOR it. Okay, so this is the Plotkin, and you can see basically keep doing the same thing at each node in the tree.
The output is not a bit, so how do you keep doing it?
It's you can keep doing for each coordinates. The length keeps doubling. You can see. You take 2 bits, you get a vector of length 2. You take 2 bits, you get a vector of length 2. And for if you have vectors, we just do coordinate wise because it's a linear operation. You can do it. If you use a vector, B is a vector, you do U XOR coordinate. And you can see length keeps doubling, and then it would be a power of 2. So that's the case for Reed-Muller and Polar codes. But so this is how the encoding structure for both Reed-Muller and Polar codes looks like. And this Kronecker operation is nothing but the binary tree kind of a structure. There are some other bells and whistles. I'm not getting into freezing and stuff, but this is like Yeah, this is how it looks like.
So this is how we should think of the encoding function.
Encoding function.
And the thing that you're looking for that is not in a general setup would be what is inside the transform that's inside the boxes.
Yeah, this is what I'll next just immediately say. So, this is because this is the way, one practical way of looking at it. Of course, there are many viewpoints you can think of it from a generative matrix point of view or other, but at the end of the day, our task is we want to design and build something. So for that, we need a specific viewpoint that allows for it, and this is one viewpoint that allows you to design new code. Because we want to rely or anchor on some structure, right? So we want to find certain way through which we can build something, and this is one practical way we found.
This doesn't fully specify even the read model or the polar. Read model, polar, you run this, and essentially you get the complete the Hadamard code, and then you have to tell which subsets of coordinates you're going to pick up.
So that's the point I did not mention. In a typical Reed-Muller polar, you freeze certain leaves. That's it. You freeze certain leaves to be 0. Let's say, just for sake of argument, let's say these two leaves are frozen, and that gives you one Reed-Muller code. Or whatever bits you want to send, they come only here 0, 1, 1, 0, 1, 1, any combination. That actually fully determines the Reed-Muller code. For polar code, maybe some other order of leaves, something. As long as you fix the leaves, this gives. This I didn't want to go into this because there's too many details, but at the end of the day, if you exactly get an actual Reed-Muller code and the polar code using this. Okay. But for now, you can think there's nothing clearer than we are building like one code or something other than that. But this is the actual encoding structure behind Reed-Muller and polar codes. And okay, so this is how it looks. And the main idea through which we want to generalize the structure is, as Rahul already pointed out, we want to parameterize this transformation blocks. Right? Instead of Plotkin, we want to use something fairly general, so to speak, in the sense it can be any nonlinear mapping, any real valued mapping. As you can see, Plotkin is a strictly binary mapping and also linear mapping. And we wanted to something fairly much broader class of mappings. So for that, how we parameterize this theta is Plotkin plus some neural network. Okay, and I said Plotkin is a binary, but if you think about it plus minus 1, you can think of everything is plus minus 1. So this addition is over the real space. Okay, it's actual real valued addition. Everything is 1 plus minus 1 in the Plotkin case, and you add some neural network on top of it. So this is how I'm parameterizing my theta.
So this will be essentially you will be moving out of the space of linear codes.
Yes, I want to move out of.
No, but why is that a design choice? Because do we know any properties that nonlinear codes achieve, which linear codes don't achieve, which linear codes can't achieve? Why would one want to step out of the world of linear codes?
So very good question. It does. I think one could approach it from various points, but for us, the main motivation was that. I agree, linear codes are already good, many achieve capacity indeed, like they're very good. But the question is, if someone gives you that freedom, if someone gives you that space or room to maneuver, can you decide?
Suddenly as such, linear codes is a large space to explore, and now you're saying, I don't know how to explore that space, I'm going to make the space even larger and I'm going to search in this.
But there's an efficient way to go about finding these codes, right?
Okay, that I don't yet see. Okay, go ahead. Yeah.
At least there's one parameter. I'm not saying you can cover the whole thing. That's also not my goal.
Okay.
I'm trying to find a specific way of finding nonlinear codes that are good, right?
Okay.
And this is, I'm giving you a way to do it.
Okay, is that parameterized by a single, like every box would be a single theta? Like how many variables?
Okay, good question. This the way I'm doing it is at each level there is only one level. In general, you can do all the nodes being the same, but the choice we made is at each level it's same neural network. Basically, the functionality at fixed depth is the same. That's the intuition, and and it's just depth is not that, it's log n. So, and this is the specific way we parameterize, and you might wonder why did you need this, or I mean in general I could just drop Plotkin and use neural network, right? And that's where the actual inductive bias shows up. And actually, we needed it is if we didn't use it, in the end again it's a disaster basically. It will end up something worse than inflation. So you need to make the right index to bias choices at the right places. So that's the reason I wanted to show how we parameterize this. This is how we parameterize this, okay? And put this for the encoder. For the decoder also, you have similar tree structure using successive cancellation and all.
So I'm very unfamiliar with some of the optimization things that you're saying, but suppose that you didn't put Plotkin in. Isn't there a possibility that your neural network will actually discover
In principle, so very good. So that's what good. So in principle, neural network can represent anything. Right? It can represent everything under the sun, right? Like the universal approximation property. Every function it can represent. But learning is a different ballgame.
Yes.
Can you learn it? Go and learn it. It's a different kind of. Given this kind of the way you're training it, there are many many nooks and alleys that we are taking it through. And in that journey, can it end up learning it? And most often we find that it's not. You do need specific hand guiding at specific places. Not all the places, but at some right points, you will need that specific hand guidance.
Should I think of this as an initial starting point?
That's exactly the way to think about it. To begin with, I'm already starting with a very good code. And on top of it, I'm trying to find how far I can go ahead. At the same time, just to answer, this does not mean that I will end up finding a good code better. It could be possible that linear codes are already good. Like there's nothing better out there. This entirely could be a fact out there sitting that there's nothing better that exists in nonlinear code that doesn't exist in linear code. That could entirely be true, but we don't know it. We want to see if that's true or not, at least through some practical way.
So the beta operation still takes two real numbers to two real numbers.
Yeah. It's everything is real valued and non-linear at this point. 0 1s you can think of plus minus 1 and everything is. Okay, so putting all this together, this is how this encoder looks like. So basically what all happening in the encoder, I'm just putting it as just for an abstraction, but this is what happens in the encoder. Decoder also you can do a similar thing using this tree and you parameterize properly everything. And that basically gives you a parametric family of encoder and decoder pairs. And this is what I'm trying to resolve my code.
And why is it parametric?
Because I'm using specific neural network parameters and all to. Okay, so yeah, and you're trying it, and yeah, this is the structure I impose on my neural network. That's what I get. And yeah, you let it try, and you hope that something good comes up, and that's at the end of the day, it turns out that we do indeed get some non-trivial properties out of the course that we learn, and they do exhibit so many interesting phenomena that I will briefly talk about.
So you will need to modify the loss function then, because otherwise it should just give you identity.
Sorry, can you repeat?
You will need to modify the loss function.
No.
No, because the channel
The channel is.
Sorry, I didn't specify, but channels for this I'm using the additive white Gaussian mask, AWGN, fairly generic channel and known to be that's very good properties. But in the case, I need a differentiable channel if someone, because I have to pass my gradients through it back to this. You can see there's a flow of information one way, but if you want to train it, there's a backward flow and backward or something. So I need a differentiable channel. So for BSc and BAC, it's a bit tricky how we want to train. There are workarounds around it. People use something called straight-through estimator or something. If you have something non-differentiable, you assume something about the gradient and train it. People still do it, but we didn't fully. Yeah, but this is for head to white Gaussian channel, which is very important and difficult channel to do well. Okay, so now I'll show about evaluation of KO codes in different settings. The first setting I consider is K. The code dimension is nothing but K, 46, and the block length is 512. So the rate is, I'm focusing on relatively low rates. This is like 1/10 roughly. And so on the x-axis, you see the range of signal to noise ratios for the Gaussian noisy channel I'm using. And the y-axis is exactly this beta. This is cross symmetry loss, but yeah, beta rate you all know. And so as you see here, so Yeah, the blue curve corresponds to the Reed Muller and the red curve to the Reed Muller. So this
The channel is AWG.
AWG, everything, every parameter is the same for both the curves.
So no, that's fine, but the channel is basically, if I'm viewing it from the RM point of view, there is a bit, the Reed Muller encoding being sent. KO codes I don't know because that's the output of your neural network. So RM code, there's a Reed Muller encoding happening. So there's a sequence of bits. Now, what you're doing is adding additive Gaussian noise at individually at each bit.
Yeah.
This is what's coming out. The decoder has to handle this.
Yeah.
And then what's the decoder you're going to use for?
We are using the same class for like.
No, what's the decoder you use for? For KO, your algorithm, the neural network is coming up with the encoder decoder pair.
Right.
For RM with AWG and noise,
Right.
what is the decoder being used to plot that line?
So for the decoder, we use a Doomer successive cancellation decoder.
Okay.
So basically, the way to view it is, I fixed my encoding complexity, I fixed my decoding complexity or architecture. Given this constraints, how well I am able to do on top of it if I can discover broader class of nonlinear and real valued code. Okay, I'm fixing the complexities. Whatever you see, because for the code, for my code to design, you need an existing encoding tree structure. So the tree structure is fixed. Once the tree structure is fixed, all I'm changing is the functionalities in the inside the tree nodes, so to speak. But the essential skeleton, tree skeleton is the same on the encoding and the decoding front. Okay.
So in the exercises you're guiding the SNR, right?
Yes.
So you're training the network for each SNR?
It's a very good question. This curve, in principle, one could do that, but this curve is something that's trained at I think minus 10 dB. I train it only at one SNR, but test it on across a range of SNR. So in that sense, very robust to changing the noisy.
I don't. The y-axis I follow. What is the x-axis?
It's a signal to noise ratio.
But what is that?
So if you have a AWG channel with Gaussian noise 0 sigma square, let's say x is just plus minus 1. SNR is minus 20 log to the base 10 sigma dB. Okay.
Does the KO code produce plus minus 1? Or we produce real numbers, right?
No.
This one I done is like, then how do you import? So
for KO,
average.
very good question. For KO code, we have the constraint norm is.
How do you impose it?
Oh, it's a scale. So if you get a real value.
Codewords could all be, I mean, you may end up with codewords which don't all have the same norm, right? So you just going to project them on.
So the nice way to look at it is Reed Muller codes if they lie on a rectangle, KO codes they lie on a sphere.
Usually there is no guarantee that they would lie on a sphere, right?
So what I call my KO code word is after normalized.
Okay, you project them on.
Yeah, always. And then I will get a real value Euclidean vector. My KO code word is a normalized version because I have to, under the same power constraint, I have to compare, right? Otherwise, I can blow up and.
No, but I find something because RM codes are conjectured to be achieve capacity under binary symmetric channels. And there are several proofs for various type specific channels. And AWGN is also one such channel. So in that case, I should not notice a gap between.
This is finite block length. Finite block length, this is generally a different ball game compared to asymptotics. Even for example, polar codes, asymptotic, yeah, they achieve capacity, but finite block length, they are known to be not that great if you go to.
No, but most of these, I agree with that. Like right now, the RM results are very bad, but polar and all that, after the Guruswami Zhao polarization things, that very quickly it's not possibly at 100 and all, but very quickly they achieve the polarization results show that they begin achieving capacity very fast. That's why you have.
No, but it was
no, here with Reed Muller, it's conceivable that the current results are, but I find it very suspicious that there's a gap in Reed Muller that I would observe.
I'm sure for polar also there are.
Okay.
But this might just be saying that there are codes that look like Reed Muller, which does nearly slightly better than Reed Muller, but they both achieve capacity.
Both achieve capacity. You will not notice.
Yeah, you will not notice it because you are at some fixed block length right now.
Okay.
Also, the rate is very low here, sir. And most of the time we don't work in.
Because the rate is.
Rate is low rate, and the reason why we choose low rate is that way one of the regimes where polar codes have been actually been maintained for this very low rate control.
The low rate, something like things like this happen. They are not.
The statements which I'm saying are not too very low.
I'm not sure there.
They are too only every constant rate. Then I don't know if they're even, I don't even know how to formulate them at low rate. Yeah, okay.
It doesn't this matter, in one case you have spheres, in the other case, by definition, you are going to work, like a cube, right?
Right, the read model.
Don't we lose because of the shaping?
So we tried lowering the scaling,
Mhm.
like not plus minus one, but you can lower any scaling as long as you satisfy the norm constraint. We didn't observe any change.
Vinod's question, the loss entropy function, I can understand it when it's the message is coming from plus minus one to the power block length. When they are coming from real numbers, what is the corresponding loss entropy?
Those messages are always plus minus.
Messages are always plus one. Okay, fair enough. Okay, got it.
Okay, so this is what we observed for 512, block length 512. A similar phenomena we observed for 256, just that the gap reduces slightly. Could be possible that there are much more bigger gains with longer block length than shorter block length. So again, this is for low rate phenomena.
And one other thing that has changed from the previous picture is that the rate has also increased. Your block length from the previous picture to this picture.
But if I remember correctly, we played around with this thing, rate a bit. I don't think it's that drastic. I don't think it's a rate, it's a block length thing.
I see.
I think we did change around, we did lower the. I'm showing you the highest rate I could get this curve for. If I'm breaking the fourth wall, yeah, this is the. Yeah. Because it does get quite complicated to train, even if you.
Does it matter how much you train?
Sorry?
How much you train the network, does that affect the results much?
How much I train, I mean, at the end of the only thing that we can look at, not even the curve, it's just the loss function. That's like the, like if it's getting, there's no like a definitive science for when you stop, this is like, in some sense, dark arts basically, like when do you stop.
After how it looks kind of.
Yeah, that. Sometimes what happens is for thousands of iterations, it stays flat and then it drops. So this is like something, basically you let it run overnight or something, you wake up in the morning and feel something happened. That's it's not always definitively you can say it's because loss is highly non-correlated. So this is the phenomena we observe for 256. And yeah, as I've shown, for if you fix the encoding and decoding complexities, these codes do show that at low rates and the short to medium block lengths, you can indeed do better than read-muller codes. And a similar picture we observe for polar codes as well. This is for a block length 64. And so one interesting point coming back to your question is, so here blue curve is polar code with successive cancellation of this decoder. And with math, of course, you do get better. This is the green curve. But as you see for KO code, this is a KO code and KO decoder. You can also do KO code with map, meaning I fix the encoder, decoding I will do map decode. Okay? And I see that the curves, both the curves match and they don't change. So in some sense, decoding is learning some nearest neighbor-like properties in a very parametric way. If you remember, decoder has a very specific structure, but it's in some way this property is getting somehow crept under the architecture somehow, or it's learning. I don't know how. It's the architecture, but it's able to learn a decoder that is as good as if you have done math. Okay, so this is the main thing that I wanted to show. Yeah, for a specific regimes, you can indeed outperform classical codes. I did not show in the results, but even if you change the channel, you try it on AWG, you keep testing on fading, bursty channel, it does still well. The same code, it does work very well. As you already seen, robustness with regards to the noisy variations for a fixed SNR rate line and a test covers range of SNR. So this is not just specific to this scenario. People in practice have observed many times that data-driven algorithms tend to be a lot more robust than some of the heuristics or handcrafted algorithms in certain space. Okay, so this, okay. 10 minutes?
Maybe more, yeah, we started late. 15 minutes.
Just one second question. So this definition of cross entropy, the probability is coming from the randomness of the channel, or is there something else?
So the two sources of randomness. One is this message bits are random, of course. The expectation,
Yeah.
but main the randomness, yeah, from MI to MI hat, the randomness only comes from the channel. Yeah. Okay, and okay, so far I have shown only the how it performs and all, but another one of the reasons why I wanted to this also to get a insight into what these models learn and some specific well-definited framework. So what we observe is that now we tried everything. We have a table code book. What we did is we plotted pairwise distance histogram. Okay, of course, it's not we took as much random large sample as possible and averaged it because we cannot plot it for all the 2 to the 46. It's not even possible. They don't even fit into memory. As the larger code book as possible, we took and we did all the things we were supposed to do, and we plotted the pairwise distance histogram. And same for the same parameters, we did it for Riedmuller code, and the orange curve that you see is the random Gaussian code with the same parameters. What we observe is that the pairwise distance histogram, the profile looks very similar to that of random Gaussian code book, and this is a very surprising find. This is something I did not intend to or expect that these codes will learn, and the many reasons or conjectures could be why this could be happening.
How do we initialize an equation?
No, that's something learned. Initialization, as I told, so if you remember, it's plotkin plus something, right?
No, I mean like, so the parameters, how are the parameters initialized?
That's what I was referring to. If you look at the encoding structure, where neural network sits in, if you remember that block, it's plotkin plus the neural network, and the neural network is initialized very close to 0. You can say in the beginning
It's not Gaussian initialization.
it is Gaussian, but the variance is so low that in the beginning it's almost a Riedmuller code.
Okay. So okay.
Beginning, when you're starting, it's almost a Riedmuller code or polar code that you're starting.
Okay.
This is, yeah. And at the end of the training, and
What is the Gaussian code?
random Gaussian code book is each entry is generated from random Gaussian.
And you have 2 to the 46 samples of that?
I'm not generating the full code. I'm generating it's a block length 512.
Yeah.
So
So what is the encoder and what is the decoder?
This only requires the info. I think it's just picking a random, mapping it to random version number and then checking an empirical average between several pairs. That's what this part, because certainly you are not computed between all 2 power 40.
not possible. Not possible.
Not all 2 power 40, which is
Correct.
No, but the reason I was asking is for the previous graphs that you showed with Riedmuller and Theo code, can we have a line for Gaussian codes in that?
Can we have not possible because you need a efficient decoder, right? How do you decode? Of course, using a random decoder it would be not good. You want to use map decoder, it's not possible because code dimension is 46 of the rest. That's one of the Riedmuller, one of the contentions still is codes are very good, but there is no good decoder. And this is in some sense trying to get at what are some nice parametric family that can get you till the map curve. So this is what we observe in the interest of time. I will, go ahead. So this is some very interesting find, and there are many interesting reasons why this could happen, but I will, I'm happy to chat on one-on-one. So just to give a brief, impact of this work, a few of the students who worked on this, they were part of the Innovation Fellowship winning proposal, and along this line of work, there have been a lot of works that try to use similar principle for various settings like interference channels, MAC, and channels with or without memory. Okay, so that concludes the. So the main contribution is here is we design a new state-of-the-art codes that can do better than classical Riedmuller polar codes in certain regimes, driven by data-driven algorithms. So that concludes the part 1 of the talk. So let's go to part 2. So I have 12 minutes, right? Okay. So it's about learning optimal transport. So the obvious question is, what is optimal transport? So at the heart of optimal transport is a very basic question. Let's say there are two distributions, Q and T, source and target, sitting in some Euclidean space. So the goal is you want to transport this distribution to this. Okay. At the end, they are both mass 1, but the profile changes, right? As you see, the mass changes. And the goal is you want to modify it in a certain way. And yeah, at the end, in the beginning, when you start with Q, in the end, you end up with P. Or the other way to look at it, you start with a random variable Y's distributed as P. If you apply P of Y, it looks like P. So they're all equivalent, doesn't matter. And okay, this is the generic optimal generic transport map. And for each transport, I have an associated cost. So the cost is nothing but the cost of moving by to T of Y. So this is the Euclidean norm square, and I take this expectation because it's random. So this is my cost. So for each transport map, there's an associated cost. And the goal of optimal transport, as the name says, is I want to find among all the maps that push forward Q to P, the one that achieves the minimum cost. That's it.
That's the map we will learn.
Yeah. So this is the optimal transport, and it has a very goes all the way back to 18th century. Gus Vardhan, French mathematician, who came up with this formulation in the time of war, as this is actually referring to actual transport of mass, not an abstract motion. Actual transport of how you transport mass of sand from one place to another place. So this is how it started. Okay, this is the optimal transport, and yeah, I mean this has a lot of implications in various fields. And one area where this idea is deeply used is in the generative modeling or GANs. And the rough intuition is what you start with is a Gaussian, something that you know everything about and very easy. And what you want to end up with is something like an image distribution that you don't know much about, right? You can. Someone gives images, you can say these are a set of images, but someone asks you to sample from image distribution, it's not easy, right? We don't even know how images, we know how images will play, but we can't describe what images are. So in that sense, the goal of generative modeling is to sample images. Can you generate images? So this optimal transport finds a very deep application. This idea finds very deep application in many problems, like in the universe and gas, whatnot. There are too many. And many other areas like biology, where you want to learn some dynamics, how cellular function evolves, everything. So there are a lot of applications for this, and control is won a Nobel Prize, and there are 2 field medalists, so it's a very rich field. And the goal, of course, is especially in the context of machine learning and various applications, is you want to learn the.
More generally, you want to learn a coupling, right? Joint distribution. When this map may not exist from X to Y, right?
So, right, but if you start on some very generic assumptions, like one of them has density, like if you assume Q has density, you can assume because people brand solution.
Why study a distributed problem and not about general problem?
The reason is most often the way it is used is you start with something like Gaussian and you want to transform it to some complicated distribution. So
Wait. So is T or determined? Is it a function or is it a randomized function?
it's a mapping. It's a mapping that transforms. It can be potentially randomized. All it needs to is satisfy this condition. If you start with a random variable y, T of y should be
It probably definitely needs to randomize. Otherwise, the highest likelihood of Q is equal to the highest likelihood of P.
Sorry, can you repeat?
So I think T needs to be randomized.
No, not all the time.
No, but then suppose there is a point with probability 1/2 in Q, then there also needs to be another point like this.
But this is the density.
It's all about density, not about distributions.
Okay.
Measures, they're not arbitrary measures.
So the main goal here is you want to find the optimal transport. So how do you find it? Again, I'm just recalling. You have an optimal transport, and the one of the main difficulty comes here is enforcing this constraint, right? Like start with Q and end up with P. It's easy to write in mathematical sense, but something you want to learn, something you want to enforce, it's not something that easy because it's at a distributional level. For all this, if you have a profile for one distribution, you want to impose some constraint on the other. And actually, in fact, Moll came up with in 1791, but this problem didn't move much until 1940. And that's when Kondrovich actually came up with this dual formulation in Soviet Union at the time. He said that, yeah, I mean, this is all good, but let's look at it from another point of view. And it turns out it actually exhibits a very nice dual formulation. So in the dual, what you have is it's a minimization over a pair of functions under, yeah, P is here, expectation P f of x, Q some h of I, they're distributed according to P and Q. And the space of functions is constrained by the following set. It means, it says that at each point x and y, f of x plus h of y is at least inner product of x and y. So this is my space of functions over which I'm taking this. And so in practice, people do try to use this formulation, but it's not something easy because you have to enforce this constraint at every pair of points x and y in this place. Sorry,
You can just click back and change
which is a very good point. I'll just come to that next. Yeah, people in practice, yeah, they do. Like, that was like a large line of work at the time using some regularization. But as Ashok already mentioned, you can indeed simplify this problem. You can write it as a this semi-dual or whatever. The minimization of this space of all convex functions, but instead of two functions, you have f and f star. F star is the pencil conjugate. Okay, this looks mathematically nice, but on a computational front, this is also the same difficulties. How do I compute f star? I don't even know.
What is the stuff?
The pencil Vardhan conjugate.
What is that?
Like
X transpose y minus f of x.
X transpose, yeah. And yeah, this is hard to compute. So the main motivation for it is how do you get around this and still come up with a clean formulation. So that's what we exactly did. What we do is, so this f star, you can use the definition of pencil Legendre conjugate actually. The pointwise sup, you can take it out. So this you can write actually as a minimax over two functions. Both are convex. But yeah, the objective looks like expectation P something. Okay, this is well defined. And now you don't have, okay, there are convex functions, but on top of it, there are no constraints as such. You don't have some pointless inequality or something. You have a very clean last objective that you have to do minimax optimization over. And there is a way to deal with convexity. There are something called input convex neural networks that indicate that your function is out, your parametric function is convex. It's not that hard. You just keep weight 0 and use increasing nonlinearity. It's a very clear, it's not something deep result. There exists a way to parameterize convex functions using convex neural networks. So just assume that it can do it. And so yeah, this is what we do. We use this minimax formulation in order to learn the optimal transport map. And how do you get the transport map? Once you do some optimization, you take the gradient of G. This is exactly your optimal map. So this is the Benamo-Grenier result. It says that.
So you use this representation that you train it on a convex neural network.
So we use this objective. We parameterize f and g by convex neural network, and we train it. And once we train it, someone asks for a map. My map is gradient. Gradient is very easy to compute for neural network.
I think a universal theorem in this convex space that you can learn all kind of convex functions.
It's a very good question. So what we show is that this is consistent in the sense if the actual pair had an optimum, this is a feasible point, and also we also show some stability. If your optimal, what you learn is a bit different. It deviates from it. How far does the optimal transport deviate? So we do have theoretical results. I'm not talking about it. Just to keep it.
So do you know? I mean, are you assuming access to P and K, or you just have samples from it?
Okay, it's a good question. So in general practice, you only have samples from P and Q. This expectation would be replaced by empirical average. The results are for actual formulation, but in practice, yeah.
But this is a general recipe, right? Kind of.
Yeah. Yeah, this I had that slide, but I just removed for the time sake. But this idea has been used in many like persistent gradient flows, in many persistent Barry centers, and
Even along with convex neural networks.
this kind of formulation, broadly in this case, but this main idea of representing stuff, because this gives a very clean way. You can use it in any framework that requires optimal transport. You can actually use it. It's that generic. And okay. So this is a framework, and you can use it.
Does the fact that you're using convexity here have anything to do with the Grenier map convexity or nothing?
Yes, the Yeah, this is all intricately connected. Because I mean that already is here from this step to this step. You have to do from going from here to here.
A few sentences.
So you don't have any condition on the Lipschitz of effectively?
No, so that comes in Wasserstein 1.
Okay.
Wasserstein 2, the dual is like this.
Okay, so unrestricted is fine. Okay.
So Wasserstein gives the nice dual, but it's one of the hardest Okay, I didn't tell you maybe, but since we are TFR, maybe I can say this. So this loss function he used is not norm square. What Mons gave is norm, just enter norm. And it took maybe two centuries maybe until Kantrovich said that's actually a very tough case. Kantrovich said, I think I don't know if Kantrovich is the first one to do it, but he considered norm square. Norm square gives you this nice dual and whatnot. All this uniqueness, all this nice beautiful results exist for norm square. And if you use norm 2, that's what Mons did. Basically, I was stuck for 2 centuries. Sorry? I don't think Napoleon is even further. Yeah, and you get it, and this is I'll just speed run through it, but you have to believe me that that's very good. Next is the distribution. You want to transport the orange blocks into green blocks, and using our algorithm, if you learn optimal transport, so it does indeed learn to split this to the nearest blocks. You have to go to green basically. So the middle block is the interesting stuff. So it splits into 4 quadrants, splits and transports it to the nearest blocks. The same thing you observe for mixture of Gaussians, you split it into the nearest blocks. And so this shows it can indeed learn the optimal transport map. And in order to comparing with some existing baselines at the time, so this is how the baselines used to do. You can see there is some spreading around the mass. The red dots are spread all around the space. The reason is because most often they always parameterized by some continuous maps. That's how transport map is parameterized. So if it's continuous, there is no way you can split the mass, right? Because 2 nearby points will go somewhere nearby. They can't go to different coordinates. But whereas if you see in our approach, 2 nearby points can go to different points because if you recall, transport map is gradient of a convex function. So gradient can be discontinuous. So this allows for learning discontinuous maps, and this kind of feature comes up in many applications like disjoint supports and stuff. So it's a very nice, interesting feature of our formulation, and also it's robust initialization. Okay, so yeah, so that contributed that. Framework to look at it, and then associated algorithm that does very well. So that concludes the part 2 and part 3.
So my question is, this is a AFM which is unconstant, right? Without any
convex.
I mean, yeah, not any convex function. So it doesn't have any bound on the gradients or anything. So how do you train something like this in a neural network? I mean, you need some upper bound on something, right? I mean,
no, it's just represented by a neural network. The parameters could be anything, right? I'm not bounding.
They might blow up, right?
They might, if they're supposed to, they might. Like all the dictates is this objective. This objective is what determines how the parameter should behave.
Okay, but are you claiming that these parameters will always be bounded in some space?
I mean, I cannot prove it, but at the same time they do behave reasonably.
I see.
Unless the distribution is not too wacky or something.
But these convex neural networks, are they as simple as you're making them out to be? Or?
Yeah, they're not that deep. Yeah. They invented it for something else, but we found that they're actually and you just give them increasing nonlinearity. You can show that it's a convex function because
composition of
that's it. Just use a composition of increasing functions in the beginning. It's not at all deep.
But that okay, fine. I mean, so your architecture limits the kind of convex functions.
Yeah, I can say so, but the end of the day, it is always
okay. Yeah, fair enough.
Yeah. So this concludes part 2. So part 3 is where what I'm currently working on and very excited about is learning in the space of LLM. So this is something that's an ongoing work. That's why I didn't include any reference, but hopefully in 2 weeks we have a deadline, so I will put up a link. And so here the main idea. Okay. So idea, I mean, as you have opened any news article or whatever, like all the days you just see as if the end is near or whatever. So we have seen everywhere like large language models working well in every domain of space. They're doing this and that. But at the end of the day, this is all good. But the many questions remain, like what are these models doing? How are they trained? And so that's the main motivation for this project, is to understand and get inside. Like, can we say something definitive about what these models are doing and how do we learn? Sorry, what are they learning and how do they learn something? So that's the main motivation for this. And so before getting directly into that, let's take a look at how are these models trained first of all, right? They seem to be performing very well. So this classical way they trained is you take everything on the internet and also something that doesn't exist on the internet, everything, you throw it, right? There's some very big corpus. We don't know what they're trying on, but probably everything. And yeah, they just throw a bunch of data to these models and they train it, right? That's all they're doing. But if you were to understand, like there are two aspects to understanding what these models are learning, right? First of all, what are the kind of data they're being trained? And the second question is, on this data, what these models learn, right? There's a two-step thing that's going on. But if you look at the data step, there are many things. Like if you just restrict to English, if someone asks you to describe English, there are too many things, right? There's a lot of grammar, there's a lot of syntax structure, there's a Markovian structure also, in the sense the next word depends on some definitive past, and this determines the dynamics of an English sentence, the sequence of words. So there are a lot of structure in your data, and with the goal of understanding something mathematically concrete, I will in particular focus on this Markovian aspect, because that's a tractable way of looking at language, and that is also mathematically well-defined setting that can give very critical insights into how this model works. And yeah, so that's the main idea. And so using that as a lens, so the approach of the plan is the following. For the data, I would consider instead of English, I would just consider Markovian sequences, okay, binary alphabet. This is my language, okay. Instead of finite vocabulary, I just have two states, 0 and 1, and they're generated with some mark. So there's a Markovian kernel sitting. Assume there's some kernel, Markovian kernel, and with that kernel, I generate as many sentences as I want, which is infinite, but
K-gram or something.
yeah, K-gram, generate K-gram. But if it helps, you can think of 1 gram also. 1 gram. We'll start with 1 gram and we can change. But the K is like the norm that we can run, right? K gram. Larger the K, the difficult is the more memory that you are increasing. But this is my data model. And for the model, I mean the neural network model, let's say you consider this one layer transformer, not even something complex. In generic case, you increase the depth, dimension, whatnot. There are many knobs to turn around here. So this is the model. So this is like the framework that I'm using to understand and get a sneak peek, insights into how transformers work. Okay. And the reason, as I said, for Markovian choosing is very good amount of English structure could be described by Markovian. So this is the setup, and we do have some interesting results in the setting. I'll just give a very brief snippet. One, we observe that for the underlying Markov chain, you know that there is an underlying kernel, right? It's generated from Markovian kernel. But the transformer model doesn't say it. All it sees is a bunch of sequences. It doesn't even know that, first of all, it's a Markovian thing. Forget kernel. All it sees is a bunch of sentences in binary language. And we observe that this is a mathematical fact, mathematical statement, is that we can show that there exists a parametric set of weights that is actually a global minimum loss surface for this transformer architecture. You can write a specific, very well-defined loss and everything for this setup. And you can show that there exists a global minimum on this loss surface that corresponds to the true Markovian kernel, which is something we sort of expect or like hope to, right? Because then, even if it does not happen, then there's no hope that it will have something meaningful. So
you're feeding 0 ones, and there's a probability of 1 becoming 0.
Yeah, so
just that simple probability.
Yes. So
and your transform is predicting the next word, and the probability of the next word. Then
yes.
You can
Yes. So I can give maybe the data model. So this is my 0, 1. This is my data model. P, Q, 1 minus Q, 1 minus P.
P and Q are any parameters that you want, anything that you like. My Markov chain is generated according to this bunch.
And then you're predicting the probability of the next word.
So yes, good. The way the transformers work is you are given a sequence x1, x2, so on up to xn. At each position, it predicts probability that the next bit, in this case, it's binary, so just one is fine, given the entire part. So this is what a probability is. The transformer models the next step probability given the entire past. And there's a specific way this theta looks, that's the architecture that determines this architecture.
But it's not like obvious because it's attention mechanism.
It's not
So I mean that in the case of Markov model that is local minima. I mean you can find local minimum.
No, that's not obvious actually. It's a local attention. Sorry,
because of the attention mechanism that this transformer has. I mean it is only looking at the local past.
No, but this local minima is in the sense of mathematical statement, in the sense saying the gradient at that point is 0 and Hessian is a positive semi-definite. This is not obvious for sure. So what all I'm saying is there exists a theta and the loss function surface that it's a stationary point and the Hessian is and it actually the reason I know why it's not a local minima at that point theta, if you look at this Markovian kernel, actually it turns out to be marginal. So exactly this. So for this Markov chain, there is a stationary distribution, right? You can write, you can compute it. It's q by b plus q and p by b plus q. So what we find empirically is that what it learns is exactly the stationary distribution. Assume that the chain is already mixed. The state chain is already mixed. When we try it, basically it ignores the entire past. It just predicts the stationary distribution, which is the marginal in this case. So this is what the second statement means. And the switching probability high means p plus q is greater than 1, meaning you're going alternating all the time. P plus is a p gives the probability of switching from 0 to 1, q gives the probability of switching from 1 to 0. So if p plus q is greater than 1, we observe that what it learns is a.
So it's a way of computing stationary probabilities of the Markov chain.
I don't know, the saying, right? It's using a hammer to, it's a head slammer to nail it.
That's interesting.
Yeah, this is something totally unexpected. First thing is something we hope, otherwise then it
What you mean is there exist local minima that are not global minima.
Yeah. So, can you,
What you mean is there exist local minima that are not global minima.
yeah, I mean, yeah. Maybe that's a better way. There exists bad local minima, like there is
Missing some is what you're saying is that you're learning part instead of actually learning the next step probability.
Yeah.
A weak result rather than a strong result. Like
it depends on how we are looking at it. From a Markovian point of view, it's a weak result because you're not learning to kernel. But from a something we don't know anything about, transformer or something, but this is a totally unexpected and surprising result that it learns to ignore the entire past.
no, so if I keep other your black box transform,
Yes.
you're asking for any prediction algorithm. All it does is predict pi.
Mm-hmm.
Wouldn't I call it a bad algorithm?
It's just matching the frequency, observe the bigger frequency.
No, I'm not calling it's a bad or something. I'm just saying it does learn something like that, which is a surprising result, and this corresponds to a bad local minimum on the loss surface. This bad corresponds to the.
Let's do the something.
Yeah, but we should finish and then.
Yeah, those are questions.
Okay. Sorry.
That's that video.
So, yeah, this is the mathematical detail behind I left here, but this is what exactly you can specifically characterize. And I do believe that the very deeper phenomena, like you can change the memory and the depth, and there's a very nice interplay going on between at these intersections. So this is what we are currently working on, and over the long term, in this broader space, I'm interested in like designing theory and algorithmic frameworks to understand LLMs and in particular give more efficient algorithms and get better insights. And on the side of designing codes, I'm also interested in for much more complex settings like channels with feedback and multi-terminal settings. How do we use data-driven methods in order to design next generation code? So this is my long-term interest. And yeah, with that I conclude. Thanks a lot for your attention.
we had questions, so maybe we can finish and those who want to ask can stick around.
Viewing the ability of transformers to learn how to change better than.
Should I stop this video?
Evaluating a transformer by substituting the Markov change.
No, that's my, I mean, the credit goes to Sharon.